Okay, so here we have our last example of finding the derivative, a formula for the derivative using the limit definition. So I will go ahead and write down the definition up here just for reference. So this is f prime of x. Okay, so we're going to set it up just like we've done the last couple problems. So prime of x is equal to the limit as h goes to 0. And then we want to evaluate the function at x plus h. So we plug in an x plus h wherever there's an x in the formula. Like that. And then we just, we have f of x. So we just use this formula right here. And this whole thing over h. And now for this type of limit, we want to clear the denominator of these smaller fractions. So we're going to multiply by 2 plus x plus h times 2 plus x. Okay, I'm going to move this over so that I maybe have a little bit of room. Maybe squish these together. Okay. Anyways, so, oh yeah. Okay, so here, what we will get when we multiply is, let's put parentheses around this so that's clear. 1 minus x, I'm going to distribute that negative, so 1 minus x minus h times 2 plus x. And then in the second part, we have 1 minus x times, 2 plus x plus h. And this whole thing over h. Okay, now, to finish off this limit, what we would do is probably multiply this out and see if we get some cancellation. Oh, I forgot my stuff in the denominator. So it will be h times 2 plus x plus h times 2 plus x. There we go. So that will be the limit that we want to take the limit of. So what I'm going to do now is do some algebra tricks, and which will make our computations a lot shorter, or at least a bit shorter. And it's okay if you don't understand the algebra tricks, because it's always possible to just multiply this out and then look for the cancellation. It's just that it would take a lot longer, so I'm taking a shortcut. But if you don't understand the shortcut, then I'd encourage you to just try to do it yourself and see that you are able to get to the same answer. And do it by just, you would multiply this out, so you do distributing, and then multiply this out, and then see what cancels. Okay, what I'm going to do is do some clever factorization. So what I want to do here is, or I guess it's not really factorization, but okay, what I'm going to do here is I do want to distribute this, but I want to group 1 minus x together and then distribute this 2 plus x, so I'll get 1 minus x times 2 plus x, and then I'll also multiply it by that h, so I'll get minus h times 2 plus x, like that. And then, okay, so that was the first term, and now in the second term, we're going to do a similar thing where we group this 2 plus x and then I distribute, so I'll put parentheses so I don't have to distribute that negative yet, and I get 1 minus x times 2 plus x, and then plus, when I distribute this to the h, I get 1 minus x times h. Okay, now the reason why I did that is because, let me just actually do this in one more step. So we get this in the denominator, it did not change at all. And so let me just write everything out. And then here I'm going to distribute this negative now. So we get negative 1 minus x times 2 plus x, and then minus 1 minus x times h, right? Okay, so what we did was basically we multiplied things out partially. We didn't go all the way. And if we do this, we can see that we get a 1 minus x times 2 plus x, and we get a negative 1 minus x times 2 plus x. So these guys will cancel, right? And then we have these two terms left, and each of them have an h in them. So we can go ahead and pull out an h from each term. So if I do that, I'll be left with a negative 2 plus x and a negative 1 minus x, right? And then we have the same denominator, but now we can cancel these h's right there. Okay, and that is what we were looking to do, so that we can just plug in h equals 0, and I'm going to simplify this numerator a bit, so we get negative 2 minus x minus 1 plus x. So we do get the cancellation of those x's in the numerator, and then the denominator will be 2 plus x plus h and 2 plus x. Okay, so we can simplify just a little bit more, and then we will go ahead and plug in h equals 0. So this is negative 3 in the numerator, and then the same denominator, like that. And then plugging in h equals 0, we get, we actually get 2 copies of 2 plus x multiplied together, so that's 2 plus x squared. Okay. Okay, so that is our answer. And right. Okay, so we're going to do obviously more of these examples in class, and I know that they're long and tedious, and that can be frustrating, but soon enough we'll have some rules that we will learn that will make this process a lot easier of finding the derivative. But we're not there yet, and I do want you to be able to use the definition itself to find the derivative of a function. Okay, so once we find a formula for f prime of x, we can plug in any point to get the slope of the tangent line to f at that point. So here, this is the function that we already, so this was from from part A of number 1. So we already computed f prime of x, and we got 3x squared minus 1. So we can write down our answer from there, right? And then if we want to know the slope of the tangent line, all we do is plug in 3. And so now f prime of 3 is equal to, this would be 27 minus 1, so 26, right? So it's just as easy as that. So instead of, computing each time, f prime of some number, we can do all of the work at once. So that was finding the actual formula, and then whenever we want to know what the slope of the tangent line is at a certain point, we just plug that point in. right? Okay, so in this case, we have g of x equals the square root of x, and so we did compute this derivative as well, and that one was 1 over 2 root x. So we get this at x equals 2, and it asks us to find the equation. Okay, so that means that we need the slope, so let's go ahead and plug in 2 to our formula, and we get 1 over 2 root 2. So this is our slope. And then we need a point on the line, so we can just plug in 2 to g, the regular function, and that will give us square root of 2. So that means that our x coordinate is 2 and our y coordinate is square root 2. Okay, so there's our point, there's our slope. We just use point slope form. So maybe I'll write it out so that we remember what that is. So y minus y1 equals m times x minus x1. That's your general form. And then we just plug in our values. So y1 is root 2. M is right here, that's the slope, 1 over 2 root 2. And then x minus, here's our x, it's 2. And then if we want to simplify, we can, or at least write it as y equals something. So probably just leave it there and not simplify anymore. But that would be the equation of our tangent line right there. Okay. Oops. So, lastly, we're just going to talk a little bit about notation. So we have this prime notation that I told you about, but there are some other ways that we might express the derivative. So if you have, so depending on the way that we want to express the function, the way we express the derivative might be a little bit different. So if your function is given as f of x or g of x or h of x, etc., we could write f prime of x, which is the notation we've been using, or df over dx. And this means the same thing. These are interchangeable, okay? And this second one is called Leibniz notation. And I think that most of the time people prefer to use the first one, but the second one is actually really nice to use as well. So there are some situations where this notation is just so much easier to write, and I think that you should, well, definitely you should know both because we're going to use both, and you should learn to like this one too. Okay, so that is if you're given your function as f of x. Sometimes you're given like y equals something, right? And in that case, we would write y prime or dy dx. So it's basically the same idea. But since we don't write the independent variable after the y when we give it in this form, it doesn't appear here either. Okay. And then lastly, sometimes we don't even give our function a name. Sometimes we just call it by its expression. So if we're just given an expression, there is a nice way of writing the derivative of that expression. So for example, if you have the function x squared, and you want to write down the derivative of x squared is equal to something, you would use d over dx of that expression. Okay, and so in this case, for this example, Yes, and put it in parentheses as well so it's more clear. So d over dx of x squared equals something like this. So notice that it's really similar to this first notation that I showed you, but there's nothing after the d. There's no thing that we're taking. So here, this is sort of the thing that we're taking the derivative of, and in the denominator, it's like with respect to the independent variable, so the x. Here, you shouldn't have anything after the d because you're taking the derivative of this expression. Okay, and hopefully we'll get more accustomed to this notation as we go along.